Swayam Prabha. Digital India. Educated India.
Hello everyone, welcome to this lecture. In the last few lectures, we have studied that how structure can be excited using impact hammer. We also saw that how we get the measurement of force and how we measure the response. We also studied FRF estimates and how to find frequency response function from the transient force and the transient signal we measured, transient response we measured. So in this lecture today, we are going to look at FRF measurement on a free beam using impact testing. So this is the setup for modal test for FRF measurement. So you can see we have a steel beam, okay, and that is being supported using soft elastic bands because we want to simulate the free boundary conditions. The beam is of rectangular cross section and the length, width and thickness of the beam as shown here, they are 750 mm, 31.5 mm, that is the width, and then the beam is 5.3 mm thick. Now the response of the beam is basically measured using an accelerometer like being shown here, this is the accelerometer, the response is measured. And then we have an impact hammer like shown here, model hammer, right, with the help of which we apply excitation on the structure. And then the output of the accelerometer and the hammer, they are being fed to an FFT analyzer. So you can see this is the FFT analyzer here. And then we require at least 2 channels in the FFT analyzer because we have 2 measurements, and the frequency response function measurement requires at least 2 channels. So it is a dual channel measurement. So let us go to next slide. Now this is the test data we are going to use. The hammer output is fed to channel 1 of the analyzer, accelerometer output is fed to channel 2, and then we have chosen 16 number of measurement points on the beam, and then we are going to perform a roving hammer test, which means that the accelerometer or the response transducer will be fixed at a particular location, okay, and then the hammer would be moved from one test point to the next, right, for application of impact when we measure the FRF corresponding to those points. The accelerometer location has been fixed at test point 10. And then we are going to use a plastic tip. We want to do model testing of the beam over a range of 1 kHz. So now before we use the analyzer to take the measurement, we need to decide the measurement setup for FRF measurement, and this basically relates to the choice of number of samples in the time domain, right, the sample length of the signal, and then the frequency range has to be fixed in the analyzer. Then we also need to decide the maximum input voltages in the 2 channels, and then we are using IEP or ICP types of the transducers, that is the accelerometer we are using, that is a IEP ICP type of transducer, and the hammer also is having force transducer which is of IEP or ICP type, and therefore these transducers require a constant current line drive supply, that is a current from 2 to 4 milliampere they need for their internal amplifier circuitry to operate. And therefore this needs to be communicated to the analyzer so that the analyzer would deliver that much current and the power to the transducers. So that also should be enabled in the analyzer. Then we also need to supply the transducer sensitivities, right, so that we get an accurate estimate of the FRF. Then we also need to decide how the measurement would be triggered, right, how it will be initiated. So that trigger setting has to be done. Then if we want to use any windows for the force and the response signals, those also should be selected, and relevant parameters need to be set. And then the kind of display layout we want, like for example we might like to have a look at the time signals, we might like to have a look at the power spectrums, or the frequency response, its phase. So, whatever we want to see, according to that we need to choose the display layout on the analyzer. Let us go to next slide. So, the first step we are going to do is select number of samples, right. So, depending upon the analyzer you use, there may be different options and settings, right. So, in the analyzer which I am using, here we need to choose in the input section of the analyzer, right, that what is the sample length of the signal, and you can see from here, for example, the sample length is 2048, right. So, 2048 number of samples have been chosen. The next setting relates to the selection of frequency range of measurement, and as we said, we are interested to measure the FRF over a range of 0 to 1 kilohertz. So, now this information has to be provided in the analyzer. So, you can see here we have taken this 1 kilohertz here. So, there would be several options. So, out of that this 1 kilohertz option has been chosen. So, the frequency range is 1 kilohertz, and we also note that here the number of samples that are also being shown here, like 2048, right. And then these two parameters once fixed, now the rest of the all time and frequency domain parameters get fixed. So, based on these selections, the record length turns out to be 0.8 second, okay, and the frequency resolution is 1.25 hertz, as also indicated here. It can be seen, that is the frequency resolution. In fact, there are 800 number of lines in the discrete spectrum. So, whatever spectrum we calculate based on these settings, there would be 800 number of frequency lines, okay. Now, we need to select the input voltages, coupling and CCLD settings. So, you can see here this in this window we can make a choice. For example, for channel 1, if we see here for channel 1, we have selected 1 volt RMS, 1 volt RMS as the maximum voltage, right, that this channel can accept. If the voltage exceeds this, then it would amount to an overload of the channel. So, this has been decided by first having a initial measure or the measurement of the force and response signals, and based on the level of the force and responses these values have been chosen. Then for the channel 2, the maximum voltage has been taken as 31.6 volts RMS. So, in addition to this, we also need to decide whether what kind of coupling is required. There are two options for the coupling, like AC coupling and DC coupling. So, DC coupling allows a measurement of the DC voltage also in the signal, right, or DC components in the signal. But if the DC component is large, then it would unnecessarily load those channels, and so therefore we go for AC coupling, because then that would remove the DC component and then the signal would be measured and analyzed. So, you can see here we have chosen the AC coupling in for both the channels, and then we also need to set the CCLD setting on, right. So, you can see here this CCLD is set on for both the channels. So, which indicates that the analyzer has to supply the necessary electric power to the transistors attached to the two channels. So, the another thing we need to set is the transistor sensitivities. So, you can see in the input section, now we are going to set the engineering units, right, and you can see for channel 1 the hammer output is being fed, and therefore the unit that has been chosen for this channel 1 is can see newtons, right, that is the engineering unit of the signal that is being received by that channel. And then we feed the sensitivity of the force transducer of the hammer in the unit section. So, you can see here in the engineering unit value section. So, here you can see we have given the sensitivity, so which is 0.001016, right, volts per Newton, that is the unit of the sensitivity. And then we also indicate in the engineering unit type section that this unit indicates the voltage per unit engineering unit, which is Newton in this case. For channel 2 also you can see the engineering unit is meters per second square, which is the unit of excitation, since the output of the accelerometer is being fed to the channel 2. So, this is meter per second square, right. And then the sensitivity of the accelerometer is, in this case the one which we are using, the sensitivity of that accelerometer is 0.01043 volts per meter per second square, and that is what has been fed here. And then the engineering unit type is volts per engineering unit type engine unit, which is meter per second square. So in this way we need to provide the correct sensitivity value data, right, and this is very essential, right, otherwise the FRFs that we get, that will not be appropriately scaled, right, and then when those FRFs are analyzed, the mode shapes that are extracted, they would also not have a proper scaling factor, right, they would be more arbitrarily scaled. So therefore it is necessary to have the correct knowledge of the sensitivity and to use that in the analyzer so that the FRFs are correctly scaled. Let us go to next slide. The next setting relates to the trigger. So we need to decide that how the measurement would be initiated, that refers to what is called as trigger, right, and in this case we are going to use channel 1, right, for deciding when to start the measurement, and that is why you can see in the trigger setting of the input section we have to convey that information, you can see here. So therefore this basically says that channel 1 signal has to be used to determine when the measurement would be assumed to be triggered or would be decided, how the triggering would be decided based on the signal from channel 1. And then the one parameter related to trigger is detection level, right. So detection level, that at what level of the signal the triggers would be set on. So in this case we have taken like around 2 newtons. So when the signal in channel 1 reaches to 2 newtons, right, 2 newton of force, then the trigger would be set on, right. And then another thing is that we also need to provide the position of the trigger, right, or means other that indicates basically with respect to the trigger condition at what point measurement has to be started. So what happens is that when the signal force signal reaches to say 2 Newton level, then before that instant also the force already is there, right, because it would start from some small value or 0 value and then reach to 2 newtons. So its journey or its rise from 0 to 2 Newton is also there, and that also excites the structure and generates the response. So we would also therefore like to measure that part of the force time history, right. So that is why we have provided here minus 18, right, which means that when the level of 2 Newton is reached in channel 1, the recording actually will be started 18 samples before that instant, right. So this would help us to cover that part of the force time history which has already elapsed before the trigger is detected. So this is very essential, right, to get a correct record of the force time history. So in the figure at the top you can see this red line, it shows the trigger level, right. So that is shows the trigger level. Now we are going to talk about any window if we need for the, let us say, the force signal. So here we are going to use the force window for the channel 1, that is which is measuring the force, right, and there are several options. For example, for channel 1 there are several options, so rectangular, Henning, flat top, exponential, force and user defined. So out of these we have taken the force window. Let us go to next page. Now we need to decide the parameters of the force window, right, what is the width of the window, when does it start, when does it end, right. So you can see here here we have taken, this is the start of the window, and we have said that at 7 samples it starts, okay, and then it ends, this is the end point, and then at 43 samples it basically ends, okay. So you can see in the figure the blue that rectangular kind of window, that is nothing but the force window. So this is force window, and this has been chosen so that the impact that is being applied, the pulse that is generated, the force pulse, that should get covered in this narrow rectangular portion of the window. That is basically the idea. So let us now try to see that what is the effect of this force window, right. So on the left hand side we have shown an overlay of the window with the force signal and before the window is applied, and we see that although the impulse that was applied has completely decayed, but even after that there is some signal which is there. For example, we see this part, so there is some noise in the force signal. So with the help of this force window, this noise can be eliminated. So on the right hand side we see the picture after the force window has been applied on the force signal, and we see that beyond the portion where the pulse is being applied or pulse is there, beyond that no longer there is any force signal, right. So all the noise which probably was there has been removed by the force window. Now we decide the window setting for the excitation signal. So we go to now channel 2, right, and then choose the window. So in this case, because the excitation signal is of decaying nature, so exponential window would be appropriate, and that is what we have chosen. So rectangular window option means that there is no window effectively, right. So if we do not want any window, then we can just use rectangular window, which means no window being applied. Whatever signal is coming in, the same signal is recorded. Let us go to next page. Now we need to select the parameters corresponding to the exponential window. So here we see that so on the top right hand side the window function has been shown. So you can see it is an exponential window function. Okay. So this window function attenuates from a large value to a small value, and the ratio of this small value at the end of the window and the initial value, that is referred as attenuation, right. So and that is something we need to choose. So you can see here in the parameter, this attenuation has to be chosen, and we have chosen a 1% attenuation, which means that the value of the exponential function at the end of the time history divided by the initial value, right, of the window, that ratio is 1%, that is 0.01, right. And then attenuation start position also has to be chosen, from what point the exponential window has to start, and that we have taken as 0, which means it starts from time t is equal to 0, right. These are the parameters we need to choose for the window function. So now we are going to see what is the effect of exponential window on the signal. So on the left hand side we have shown the overlay of the exponential window with the raw time signal, and these two are the zoomed views, right. And then on the right hand side we are showing the effect of the exponential window on the signal after the window has been applied. And now we see that on the left hand side what we see, when the window function is not applied, the signal has not decayed completely. So we can see here the signal here decay is not complete. When we take its FFT, what is going to happen? There will be some leakage. We studied in the lecture earlier, right, that when the signal does not decay completely, then what happens when we take the DFT, then signal is assumed to be periodic, right, and then because of that there would be discontinuity in the signal, and then that would lead to leakage. So on the right hand side the figure shows that the exponential window has forced the signal to decay or attenuate almost completely, right, and that helps to reduce the leakage. Let us now try to see that if we are using a plastic tip, then would it be able to allow us to take measurement over a range of 1 kilohertz. So for this you can see on the right we have the figure. At the top we are showing the force time history, right. So you can see this is the force pulse, this is the impact force pulse that is being applied by the hammer, right. And then the lower figure is about the power spectrum of the force, right, and then the y axis is in terms of the dB and the x axis is in terms of the hertz frequency of the signal. The spectrum magnitude is almost uniform throughout the range, right, which means that the signal has sufficient energy over the 0 to 1 kilohertz range, and therefore it can be used for excitation of the structure over this range. Now we choose the display layout. So we would like to have the time histories of the two channels, right, the force history and the response history, and then we will also like to see the spectrums, and that is why we have chosen a layout where we can display 4 graphs on the screen. Now we choose what kind of spectrum we want, and we have chosen the frequency response. Okay, we would like to see the frequency response, which is nothing but the FRF. So this now shows finally the measured point FRF, right. So we applied impact at the location where the accelerometer is fixed, right, same location. So the measurement will give us the point FRF, or what is called as driving point FRF. Okay, and then the signal was recorded, and the force signal and the response signal, they are shown on the in the top two figures, right, at the top. So this is the force signal, and this is the acceleration signal, right. So the lower two figures show us the magnitude of the frequency response function and the phase of the frequency response function. So this is the magnitude plot, and this is the phase plot. Okay. So in the magnitude plot, what we see is that in the close to zero frequency also there is a mode, right. That is due to the rigid body mode the system has, right, because we are testing under free condition, and so there will be rigid body modes. So we see here, for example, here we have rigid body modes, and then we have around 6 number of peaks appearing there. So there are 6 flexible modes which are there, and between every 2 consecutive resonant peaks, right. So we see one anti-resonance there, right, which is the characteristics of a point FRF, that between every 2 resonances there would be an anti-resonance frequency. So we see, for example, here this one, this one, this one, so this one. So these are all the anti-resonance frequencies, right. And of course, these are all the resonant frequencies. They are all the resonant frequencies. The phase plot also shows change of phase. For example, we see that whenever there is a resonance being encountered, then there is a change of phase from 180 degree, 0 to 180, and then when there is an anti-resonance encountered, again there is a change of phase, right. So overall it looks to be a very good measurement from the FRF magnitude and phase plot. We see that there is not much noise in the two plots, right. But let us also try to see that if we are interested to measure FRF by spectrum averaging, then how that can be done. So the first thing we need to decide is the number of averages, right. So you can see here we need to decide the count, that is the number of averages, and that we have chosen as 4, right. 4 averages we have taken for the purpose of demonstration. So let us first of all try to see the auto and auto spectrums of the 2 channels, right, and that is why we have taken, instead of the FRF, we have taken the power spectrum as the output of interest. So you can see here, now we have the force and the acceleration time histories on at the top, right, and then in the bottom 2 figures we see now the power spectrum of the force signal and the acceleration signal. So they are nothing but the auto spectrum of the force and auto spectrum. So this is the for the force power spectrum, and this is the acceleration power spectrum, right. So they are nothing but auto spectrums, and then similarly we can get the cross spectrum between the response and the forced signal, right. That would be required to find FRF. So now we would like to also see, because we are doing averaging, we would like to see also the coherence function. So we choose coherence function also as the output. So we will now have the 2 time signals and frequency response magnitude and the coherence function, so that we can see the quality of the FRF we have measured. So you can see here, this is the frequency response and coherence function when only one measurement has been taken. So you can see here we have chosen 4 number of averages, but right now this plot is based on now first measurement. So, out of those 4, the first measurement has led to these plots. So, from the coherence plot we see that the coherence is 1 throughout the frequency range, but this is actually misleading because for with just one measurement coherence will always be 1, right, because at each frequency the output and input can always be related by a linear relationship, right, irrespective of whether there is any noise in the signals or not, correct. So, now we go to the next measurement. So, you can see this is the estimate of the frequency FRF and coherence function when we have now 2 measurements have been taken. It is based on two measurements, okay, and now we see that coherence function no longer is a unity everywhere, right. So, in this way we take the third and the fourth measurement, and this is what we get at the end of 4 measurements, right. So, you can see here now this is based on 4 measurements. So, what we see in the coherence, now the coherence is low at certain frequency, and what these frequencies are? These frequencies are frequencies where there are anti-resonances, right. So, you can see this is the coherence very low value, something like say 0.3, and that is at this anti-resonance frequency. Similarly, this coherence dropping to a low value is due to at this anti-resonance frequency, and so on. So, at anti-resonance frequencies the signal level is very low, right, the response is very low, and that leads to, so if there will be some always a small measurement noise in both the signals, and therefore what happens, the signal to noise ratio becomes very poor, low at these frequencies, and because of which the coherence turns out to be much smaller than 1, right. So, but overall this is a very good measurement also, because the drop in coherence at the anti-resonance is expected, right, but at other frequencies the coherence is very good, which indicates a very good measurement. So, therefore, this completes the measurement of point FRF, correct, and this we can save, and now we measure the FRFs at other points the way we did for the point FRF, right. So, in this way we cover all the 16 points, that uses the one row of the FRF matrix, right, which is what is obtained in a roving hammer test. And these FRFs then can be downloaded from the FFT analyzer, and then they can be analyzed in a curve fitting software, in a model analysis software. So, the curve fitting and how the analysis of these FRFs can be done, that is something we will see in the later lectures. So, in this way today we looked at FRF measurement on a free beam using impact hammer. We stop here. Thank you.